And today I'm going to talk about the possibility that energy transfer can proceed quantum coherently in light harvesting systems under incoherent excitation conditions, as opposed to experimental conditions in which light is coherent. So this is a work in collaboration with Alexandra Olaya Castro, who is giving a talk next, and Greg Scholes. So I did my PhD with Alexandra, then I moved to Greg Scholes' group in Toronto for a bit more than a year and a half, and now I'm back as a postdoc with Alexandra. So we have a long-lasting scientific and also personal relation. So, well, the motivation for this work is, as you know, this evidence of long-lasting quantum coherence in light harvesting systems. And this has been observed in several complexes. So the first studies date back to 2007. And these were performed in the reaction center of purple bacteria, also the Matthew Olson of green sulfur bacteria. And the first studies were all performed at cryogenic temperatures. But then later in 2010, there were more breakthrough experiments, some in Greg Scholes' group, especially Elisabetta Colini, who was here yesterday, took part in these experiments, and where they also showed long-lasting coherent dynamics at room temperature. So all these experiments have motivated a huge amount of theoretical research and also more experiments. And the basic questions are, first, well, how can quantum coherence survive in what is commonly referred as a hot, wet, and noisy environment of chromophores? Because chromophores are these light-absorbing molecules, and they are embedded in a protein scaffold, and there's a solvent. So it's really a complex system. So how can really coherence survive here? So there are several possibilities for this. One regards having just weak electroconformal coupling. Also, maybe different chromophores can be spatially correlated, or also the paths can be temporally correlated. And then, besides that question, okay, how can quantum coherence survive? There's a question about, is this coherent dynamics of any actual functional relevance for biology? This is actually an open question. And there have been many speculations as well, even speculations about, okay, maybe the light harvesting complex performs some sort of quantum computation. There's not really much evidence for that. But the truth is that this is really an open question. Some people also think maybe evolution has chosen for these systems to work in some sort of quantum limit or evolve in a way in which they use quantum coherence. I mean, light harvesting systems, there are really tons of different antennas, so I think it's very unlikely that evolution kind of chose one specific solution which involves quantum coherence. But nevertheless, quantum coherence, in particular quantum coherence dynamics, might play a role. We still don't know which role is that, but it might be there. But then, okay, all this is very good, but all these experiments have been performed in a laboratory. So the excitation source is a coherent pulse of light. And this is very different from sunlight, right? Sunlight is just thermal, incoherent light. So now researchers are also posing the question of, well, is really all this relevant for natural sunlight incoherent illumination conditions? So before continuing, I think it's good to clarify what we mean by coherent energy transfer. So first of all, in light harvesting complexes, the absorption cross-section of chromophores is generally quite low. So under normal illumination conditions, you can assume that there's always at most a single excitation in the system. So, well, first, each chromophore can be, no, I didn't want to do that. Each chromophore can be assumed as a two-level system, and then the state of a multi-chromophoric system can be denoted just as M, in which the mth chromophore is excited and all others are in the ground state. And then the general density matrix, the general form of the density matrix describing this state, within the single and zero exciton manifold as this form. So there's a probability that the whole system is in a ground state, unexcited. And then these terms have to do with single excitations. So the diagonal terms are the populations, and the off-diagonals are the coherences. So to understand what we mean by coherent energy transfer, well, first, it's easier just to think about the incoherent limit. So in the incoherent limit, we can think that the excitation performs a random walk in the antenna complex. So basically, excitation hops from one molecule to another. And this means that we can have a rate equation for populations. Well, this should be a raw dot. This is a problem with Mac2 PC, but this is a raw dot. And basically, you have a rate equation for populations. Now, if you want to talk about coherent energy transfer, here it means that during transfer, there are also coherent evolution of diagonal elements of the density matrix. So coherent evolution of these elements. So coherences actually oscillate with some sort of well-defined frequency. Then, well, yesterday Elisabetta was also mentioning the definition by Greg Engel. So in his case, he talked more about coherence when you actually see all these oscillations also in populations. But generally, because you have coherences that oscillate, this also translates into populations that oscillate to some extent. So, well, first of all, why should dynamics be different if we have coherent excitation or incoherent excitation? So there is this very interesting paper by Paul Brummer and Moshe Shapiro, in which they compare excitation of a single molecule with coherent laser illumination, and then when the illumination conditions are incoherent, just thermal light. This is a very idealized model because it's just an isolated molecule. So there's no way of exchanging energy with a bath or anything. So in terms of the eigenstates of the molecule, they find that once the interaction between the molecule and the radiation field is turned on, then they find that the reduced density matrix for the electronic degrees of freedom has this form. So first, you have some populations. So light has populated eigenstates of the Hamiltonian, but also you have some coherences. No, okay, sorry. But then what is interesting, okay, coherent light will induce some coherences in the state after photon absorption. So then this evolves under unitary evolution. So you have just a coherent evolution of coherences. And then the interesting point is that if light is incoherent, this term here that has to do with coherences vanishes. And basically, all that incoherent light does is populate eigenstates of the system. And because these are eigenstates, these are stationary states, so there's absolutely no evolution. This, again, is an isolated system, so it's very different from real molecules. And it's actually known that in real molecules, even if you excite them with incoherent light, there are processes such as internal vibrational relaxation that take place. So this is interesting, but it's not the full story. So basically, the nature of energy transfer will depend on two things. One, it is important which is the excited state of my macromolecular aggregate. But also, crucially, it's very important how this system, how the electronic system interacts with its environment. So the electron-photon coupling, of course, plays also a very important role in how energy transfer proceeds. So the motivation of our work is really to shed light into this question about do coherent energy transfer play any role under incoherent illumination. And then because we've seen that in an isolated molecule, incoherent light excites eigenstates of the system, then we pose the related question, which is, do coherence dynamics take place after an incoherent excitation? So this is assuming that sunlight has excited an incoherent state, so an eigenstate of my system, can energy transfer afterwards proceed quantum coherently? Of course, unlike the case of an isolated system, dynamics take place, because this is an eigenstate of the system, but not of the whole system plus bath. So dynamics take place. And we know also that this is really what happens in energy transfer. It absorbs in a certain state that is not an eigenstate of the whole system and bath. Otherwise, there wouldn't be any transfer, right? But we know that energy goes from molecule A to molecule B. So this is just a picture representation of this. And in fact, here we will focus on a phonon bath that has a finite relaxation time. So it means that non-equilibrium phonon processes take place during energy transfer. And we will show that actually this kind of environment can support first the emergence of non-Markovian dynamics of excitations, and that it also supports the emergence of coherences, and more importantly, that these coherences can oscillate for a certain period of time. So this is just the general form of how to describe the excited state dynamics of a multichromophoric system. So we have the standard electronic Hamiltonian, then the bath, which is assumed as a bath of harmonic oscillators, and then the electron-phonon coupling. And one key element that will dictate how energy flows or how dynamics happen is precisely this electron-phonon coupling, which is characterized by the spectral density. So in this work, we're going to choose a smooth, continuous spectral density. This is of ohmic form. And the relevant parameters here are the bath reorganization energy that somehow takes into account the strength of the interaction between the system and the bath. And then this cutoff frequency, whose inverse is the bath correlation time. Either bath correlation time or bath relaxation time, in this case, are equivalent. So now we need to choose a suitable model to actually model the coherence due to the phonon bath. So there are two limits in energy transfer. One is the limit of strong electronic coupling, in which there are the standard Redfield equations, which are well known. Then the opposite limit is Foster theory, in which energy just hops incoherently. And then there's this intermediate coupling regime, which is very challenging, and as someone said yesterday, kind of a nightmare in a way. But on the other hand, it also captures very rich dynamics that are not captured in these other two limits. So it's actually very interesting. The challenge is, of course, how you model this. So just now to give an example of how an energy transfer, the nature of energy transfer, depends on the initial state, I just want to focus on the limit of strong electronic coupling. So this is the typical Lindblad type master equations. So strong electronic coupling, Markovian approximation, and the secular approximation. And in this case, in the eigenstate representation, so this is the density matrix for the electronic degrees of freedom, coherences and populations are completely decoupled. You have coherences that evolve, first of all, with this term, which is due to unitary evolution. And then another term that basically causes a decay of coherences in time due to the bath. And then populations of eigenstates, basically there's just hopping jumps between different eigenstates. So what is interesting here is if you start your system with the excitation localized on one molecule, so many studies do that, then you actually see coherent energy transfer. Because you have this term, and then if you look at the populations of chromophores, you will actually see oscillations. But then if you instead start with an eigenstate of the electronic system, then that doesn't happen, because there will be no coherent evolution, because you're in an eigenstate. The bath only dumps coherences. It cannot create any coherence. So again, there's no way of coherences to emerge. And all you have is an incoherent transfer between excitons. So this means that this type of equations would predict that there's absolutely no coherent energy transfer under incoherent excitation conditions. Okay, so that's it. So now, because we're interested in being able to capture these richer dynamics, and in particular non-equilibrium phonon dynamics, we're in this intermediate coupling regime. We choose the approach developed by Tanimura and Kubo in 1989, which is the hierarchical equation of motion approach, which is really good in some ways. It's good in the sense that it's a non-perturbative treatment and that can extrapolate well between these two limits. And also, it's not based on the Markovian approximation. So it does take into account these time-dependent reorganization processes of the bath. So this was originally developed by Tanimura, and lately Ishizaki and Fleming used this to study electronic energy transfer in light harvesting systems. So, well, the equation is kind of complicated, but what you have here is a set of coupled differential equations with many different density matrices. One of those density matrices is the reduced density matrix of your system, and all others are just auxiliary density matrices. And these auxiliary density matrices, what they do is that they capture the memory in the bath. So they are kind of keeping track of what the bath is doing. And well, basically all the parameters here are just come from either the electronic Hamiltonian or the system bath coupling. And then of course temperature is also embedded there in beta. So now why are non-Markovian dynamics interesting? If we have non-Markovian dynamics, we have a system interacting with a bath. We know that in general, when you have a bath, information or coherences or any sort of information flows from the system to the bath. But when you have non-Markovian dynamics, then some of this information can flow back to your system. And it's currently an issue of how you quantify, and you can really determine whether there are non-Markovian dynamics or not. So one way to witness non-Markovian evolution is through this measure, which is called the distance measure. And this tells you how far apart two different density matrices are. So under Markovian dynamics, two states will always become closer during the evolution. But if non-Markovian dynamics take place, then during the evolution, the distinguishability between these two states can actually increase at certain periods of time. So if we witness that, then it means that non-Markovian dynamics are actually taking place. So later we will try to determine to what extent we are observing non-Markovian dynamics.
So you said that under Markovian dynamics,
yeah,
the two states become closer and closer, right?
Yeah, so these measures, so the trace distance.
But that comes from the fact that if you have a quantum operation, then it's always, it tracks. Yes, the number. Oh, okay. That is the trace distance.
Yeah.
Kind of the...
So this is the trace distance. So basically, that is a quantity that is maximum if you have orthogonal states, and then it's 0 when you have equal states.
The larger t is, the closer the two states are, right?
So the larger d is, the more distinguishable they are. But when the distance is 0, it means that they are exactly the same. Yeah. So then if you see that at any point of the evolution, this distance is increasing rather than decreasing, which is what is expected under Markovian evolution, then this is a witness for non-Markovian dynamics. So in particular, it's good to focus on the derivative. So if this derivative is positive, then there are non-Markovian dynamics taking place. So as a model system, we're going to choose these experimentally motivated light harvesting complexes, which is the PC645 complex found in cryptophyte marine algae. So Elisabetta was actually mentioning this particular complex yesterday. And because our calculations are numerically heavy, so for simplicity, we're going to just choose a subunit. So the whole complex is 8 chromophores, but here we're only focusing on 4. Particularly, we're focusing on the 4 chromophores with the highest energies. And we are including this dimer that Elisabetta was referring to yesterday, which is a strongly interacting dimer. So there is a strong coupling between these two. The other couplings are relatively weak. So if you diagonalize this electronic Hamiltonian, you get these eigenstates, and then just the representation. These are site energies of the individual molecules, but then because they are coupled, in particular this central dimer, this gives rise to this splitting in which you have now delocalized excitons. So this one's the DVB plus, DVB minus. It's almost like a symmetrical or antisymmetrical superposition of the molecular sites. And as I argued before, we're interested in following dynamics given an eigenstate of the electronic system and see if coherent dynamics actually emerge or not. And the state that we choose is the third exciton here. And this is an optically bright exciton. So that's why we decided to choose this one. So here, we performed the simulations with the hierarchical equation of motion approach at room temperature. And here I plot the coherences in the exciton basis for different parameters of system bath. Here it's not very clear, but basically this here has the reorganization energy and the bath correlation time. And they are all here for different values. So in all of these cases, what we observe is that initially there are absolutely no coherences, of course, because we started with an eigenstate. But then what is interesting is during evolution, coherences actually emerge. And not only they emerge, but they oscillate for a certain period of time. So in general, for example, if we compare these two cases, these two have the same reorganization energy, but this one has a cutoff frequency which is smaller, so that translates into a longer bath relaxation time. And in this case, the coherences oscillate slightly longer. And then another thing that is interesting is if we compare, for example, these two, they have the same bath correlation time, but this one is a weak system bath coupling. In this case, the magnitude of coherences are actually much smaller than in the case in which you have a stronger coupling to the bath. And now, because we want to determine to what extent non-Markovian dynamics are taking place here, we plotted the trace distance for the different bath parameters that we considered previously. And here we have the derivative of the trace distance. So as I mentioned before, any increase of the trace distance is a signature that non-Markovian dynamics are taking place. So it's particularly interesting to have a look here in which I have all the instants in time in which this derivative is positive. So all the instants in time in which the distinguishability between two different initial states is increasing. And if we, for example, look at two curves with the same bath correlation time, so for example, the red and the green, we see that here in both cases, non-Markovian dynamics appear, and here as well. The green is there, it's extremely small, but it's still there. And if we compare now the other two cases with the same bath correlation time, which is the pink and the blue, this only appears here at the beginning, but then there are no more revivals of this non-Markovian evolution. And in fact, these timescales are comparable to the timescale of bath relaxation time for each of the simulations.
But the results are the same if you change row 1 and row 2? Or?
Well, no, if I change row 1 and row 2, sometimes I don't even observe that. To be honest, to have a proper measure of non-Markovianity, one would need to take into account all possible pairs of initial states and then basically add up all that. Because the simulations are very expensive, I cannot do that. But this is, rather than being a measure of non-Markovianity, it's just a witness. So that is the point. So, and in general, when we had a larger bath relaxation time, we observed previously that coherences lasted a bit longer. And here we also observed that this correlates with a revival of non-Markovian dynamics for a longer time. So we really see that, at least qualitatively, there is a relation between this emergence of coherences and coherent evolution and this non-Markovian dynamics. So, well, our explanation of why coherences emerge and coherent dynamics emerge. First of all, coherences emerge because we start in an eigenstate of the electronic Hamiltonian with no correlations with the bath. But then during the time scale of bath correlation time, system and bath become correlated. And this correlation or this interaction actually induces coherences between excitons. So it is reasonable that coherences appear. And now these oscillations, well, basically they evolve under some sort of effective electronic Hamiltonian. It's not exactly the electronic Hamiltonian because you have the bath, so it's renormalized to a certain extent, but then you have that. But then what happens is as the bath equilibrates, then what dominates is just relaxation and dephasing due to the bath. So in a way, the bath is creating these coherences. It allows them to fluctuate for a period of time, but in the long term, still it will damp this. And also to understand this issue about correlations forming between the system and the bath, we can go to the limit of the weak system-bath coupling, so basically this here. And in this case, you see that in the long time behavior, exciton coherences actually diagonalize the density matrix. So in this case, we can assume that throughout evolution, system and bath are approximately uncorrelated. And that is why the coherences that we observe are actually much smaller. And now, well, because here we were just looking at coherences, but how do these coherences actually translate into populations? So in this case, I plotted exciton populations, and we do see that there is also some oscillations in the exciton populations. I've also plotted this in the site populations, and there you even see more oscillations than this. And if we want to somehow compare the time scale of coherent oscillations, those have a dephasing time of around 200 femtoseconds. And to compare it to something which might be physical or relevant for transfer, we calculated this transfer time in which half of the population of the donors has been achieved. So the donors are the MBVs, and about this time of about 600 femtoseconds, about half of the population of these has been reached. So still, this dephasing time, it is slightly lower than this transfer time, but still they are not so different. So the main conclusions is that we have shown that if we couple the system relatively strongly, but well, not too strongly either, but to a slowly relaxing bath, this will induce non-Markovian evolution of excitation, of electronic excitations, and this will support the emergence of coherence and of coherent energy transfer from an initial state that has no superpositions. And then we expect that other mechanisms that support non-Markovian dynamics can actually have the same effect. So starting from an incoherent excitation, then coherences and coherent energy transfer can emerge. And this, for example, can be very important in cases in which you have your electronic system interacting with discrete vibrations, strongly coupled to discrete vibrations, which is the work that that Alexandra, or the situation that Alexandra is considering. Also, we can think that maybe these incoherent initial conditions are relevant when you have a transfer from one antenna to another antenna rather than just absorbing sunlight. And, well, and the main question, whether this coherent dynamics are relevant or not for the functional role of light harvesting systems, it's really still an open question and it's unknown. And it might be that if we want to somehow assess the relevance of coherences, we need to look into other performance measures, not only efficiency that concerns populations, but maybe other sort of performance measures that takes into account coherences. Just to finalize, I would like to acknowledge the group of Greg Scholes in Toronto, Alexandra's group at UCL, and also, of course, funding that supported this research. And thanks.